Hello, and welcome to the session on prime factor decomposition. What are we going to learn in this session? First, we'll understand what do we understand by prime factor decomposition. Then we'll know the two methods to uh, carry out prime factor decomposition for any number. And finally, we'll understand how do we apply prime factor decomposition to find HCF and LCM of different numbers. So let's get started. The first big question to answer is what are prime numbers and what are prime factors? Well, you must have learned about this definition in your school. Prime numbers are numbers which have exactly two factors, itself and 1. Examples of prime numbers could be 2, because 2 has only two factors, 1 and 2, or 3. 3 again has two factors, 1 and 3, or 5. Once again, only two factors, 1 and 5. There are many such numbers which have two factors, and all of them are prime numbers. 2 is the only even prime number amongst them. What are prime factors then? Prime factors are factors of a number that are also prime. Simple. Okay, factors of a number that are prime numbers. For example, if you realize I can split the number 10 as 2 times 5, and 2 and 5 are both prime numbers, and hence 2 and 5 are prime factors of 10. Likewise, 21 can be split as 3 times 7, and 3 and 7 are prime numbers, so they qualify as prime factors of 21. Finally, 35 is split as 5 times 7, so 5 and 7, because they are prime numbers, they become the prime factors of 35. So what is prime factor decomposition? Prime factor decomposition is a method to express a number as a product of its prime factors. A method to express any number as a product of its prime factors. For example, 15 can be written as 3 times 5. That simply is prime factor decomposition of 15. 12 can be written as 2 times 2 times 3, right? 2 times 2 is 4, 4 times 3 is 12. So 2 times 2 times 3 is a prime factor decomposition of 12. Likewise, we can write 8 as 2 times 2 times 2. So that is a prime factor decomposition for 8. Now sometimes we can always write prime factor decomposition in an index form. When does that happen? When there are more than one of a particular prime factor. For example, in the number 15, we have 1, 3 and 1, 5. So we cannot write that in the index form. However, if you look at the number 12, it has 2 2s and 1 3. So we can write that in the index form. You know what are index laws, right? Laws of indices. So 2 times 2 can be written as 2 squared. So we can write 12 as 2 squared times 3. How can we write 8 then? It has 3 2s, right? 2 times 2 times 2. So we can write 8 as 2 cubed or 2 to the power of 3. Finally, the big question, how do we decompose a number into its prime factors? As I said at the beginning of the lesson, there are two methods of doing that. The first method is called the factor tree method. In this method, we try breaking down a number into its factors, okay, such that until the end of each branch of the tree, you will end up getting prime numbers. Okay, let's have a look at it. Let's say 20. So let's first break down 20 into two numbers. So 20 is 2 times 10. Because 2 is a prime number, we'll not break down that particular branch further. However, 10 is not a prime number. So we'll break down 10 as 2 times 5. And incidentally, 2 and 5 are prime numbers. So what we have now is we have prime numbers at the end of each branch of that factor tree. And hence 20 can be written as 2 times 5 or 2 squared times 5. Now what is interesting is you could have broken down 20 in any other way in the initial breakup, and still you would have ended up getting the same answer. For example, in this particular case, we broke down 20 as 2 times 10. What if we break down 20 as 4 times 5? Would you end up getting the same answer? Let's see. Now, as you can see, when I break it down as 4 times 5, 5 is a prime number. So we don't touch that branch of this particular tree. But 4 is not a prime number. So we can break down 4 further as 2 times 2. And 2 and 2 are prime numbers. So as you can see, now we have prime numbers at the end of each branch of that tree. So 20 is again the same 2 times 2 times 5. As you can see, it's the same one as what we got earlier, or 2 squared times 5. So how you break it down initially doesn't matter. As long as you keep breaking it down further and further, and you end up getting prime numbers at the end of every branch of the tree, you will finally get the same answer. Let's take some more examples about this. So how do we decompose 60 into its prime factors? 60 can be broken down as 6 times 10. Now, incidentally, neither of them is a prime number. 6 and 10, neither of them is a prime number. So you break down 6 as 2 times 3. We break down 10 as 2 times 5. And incidentally, we have prime numbers at the end of every branch now. Now we can write 60 as 2 times 3 times 2 times 5. However, as a convention, we always write the prime factors in ascending order, which means from smallest to biggest. So the way I will write this is 2 times 2 times 3 times 5, because 2's are smaller than 3 and 5. So we'll write the 2's initially and then follow it up with 3 and 5. Or in the index form, we can write it as 2 squared times 3 times 5. How do we decompose 100 into its prime factors? Let's split 100 first as 10 times 10. Now, neither of these 10s are prime numbers, so we need to split 10 further as 2 times 5. And each one of them will be split as 2 times 5. Now, let's put all the prime numbers together because these are all prime numbers. So we'll put all the prime factors together and write them in ascending order. So it will be 2 times 2 times 5 times 5. Or in the index form, it will be 2 squared times 5 squared. How about 84, right? 84 can be split as 4 times 21. Now, neither of them is a prime number. So we split 4 further as 2 times 2 and 21 as 3 times 7. Now we have all the prime numbers at the end of the branches. So we'll put them. Incidentally, they're already in order 2, 2, 3, and 7. So that's what it is. 84 is 2 times 3 times 7, or 2 squared times 3 times 7. I hope you understood the factor tree method for decomposing numbers into its prime factors. The second method is the ladder method. In this ladder method, we write the number and write an L-shaped formation below it. Now, let's look at small prime numbers and try to find out whether that goes into 60. For example, the smallest prime number is 2. So does 2 go into 60? Is it divisible? Is 2 a factor of 60? Yes, it is, right? So 2 divides 60 30 times. So we make one more ladder. So it's like a step of a ladder, as you can see. Now, 2 is also a factor of 30, and it can divide 30 15 times. So that's your next step of the ladder. Incidentally, 2 is not a factor of 15, so it cannot divide 15. So let's go to the next bigger prime factor, which is 3. 3 divides 15 as 3 times 5, and 5 divides 5 as 5 times 1. So you go all the way down this ladder until you end up getting 1 at the bottommost rung. Now you multiply all the prime numbers that you can see at the left hand side of the ladder. So 60 can be written as 2 times 2 times 3 times 5. Now this is what we call as the ladder method, right? 2 squared times 3 times 5. Let's take one more example. Okay, how about 24? 24 can be divided by 2, which is the smallest prime number, and 2 divides 24 12 times, correct? Once again, 2 divides 12 6 times, and 2 also divides 6 3 times. Now 3 cannot be divided by 2. However, 3 can be divided by 3 itself once. And that's it. We got 1 at the bottommost rung of the ladder. So your final answer is 24 can be written as 2 times 2 times 3 times 2 times 2 times 2 times 3. And that's your prime factor decomposition of 24. 2 cubed times 3. Well, now how do we use prime factor decomposition to find HCF and LCM of numbers? Okay, let's have a look at that. So the example is find the HCF of 18 and 24. Although the question says find the HCF, we'll also find the LCM. It's like shooting two birds with the same stone. Okay, we find HCF and LCM with one go. Let's see how this can be done. For that, the first step is to find the prime factors for 18 and 24. So let's decompose 18 and 24. Let's begin with 18. 18 can be split as 2 times 9. 2 is a prime number, but 9 is not. So 9 can be split further as 3 times 3. And now we have prime numbers at the end of each branch of the tree. So 18 can be written as 2 times 3 times 3 or 2 times 3 squared. Let's decompose 24 now. 24 can be written as 4 times 6. Neither of them is a prime number. 4 can be split further as 2 times 2 and 6 can be split further as 2 times 3. Now we have all the prime numbers at the end of the branch. So 24 can be written as 2 times 2 times 2 times 3 or 2 cubed times 3. Now, you would have understood this step. This is the initial step, prime factor decomposition. We are all aware of that. So 18 is 2 times 3 times 3 and 24 is 2 times 2 times 2 times 3. Now, how do we use these prime factors to find HCF and LCM of these two numbers? For that, we need to construct a special diagram called Venn diagram. Are you familiar with the Venn diagram? Well, it consists of two circles which are overlapping. One of the circle comprises of prime factors of 18 and the other one comprises of the prime factors of 24. And the overlapping region comprises of the prime factors which are common to both 18 and 24. The first step is to put the prime factors in the common region. So if you look at the prime factors of 18 and 24 on the left, which are the common factors in both of them? As you can see, 2 is a common factor. So let's put 2 in the common region, the overlapping region. We can also see 3 is a common factor, right? So let's put 3 as well in that region. Now, if I look at the number 18, what factor is left out? Okay, if I leave out the common factors which have been circled, the only factor which is left out is 3. So that goes into the uncommon region of 18. So it's a part of 18, but not a part of 24. So it's not common to 24. Likewise, if you look at the number 24, apart from the common factors 2 and 3, there are two factors, which is 2 and 2, which are uncommon. So these twos go into the uncommon region of 24. So you have laid out the Venn diagram for prime factors. Now, how do we find the HCF and LCM? The HCF is the product of all the prime factors in the common region. So if I look at the common region, it has a 2 and a 3. If you multiply it, 2 times 3 is 6. That is the HCF of these two numbers. While the LCM is a product of the prime factors which are there together in all the regions put together. Okay, so if you look at all the prime factors inside the Venn diagram, we have a 3 times 2 times 3 times 2 times 2, and that is 72. Right? 3 times 2 is 6, 6 times 3 is 18, 18 times 2 is 36, 36 times 2 is 72. So the LCM of 18 and 24 is 72, while the HCF is 6. Let me repeat it again. For HCF, we only multiply the prime factors in the common region. In this case, it is 2 and 3. Whereas for the LCM, we multiply the prime factors, which are all of them inside the Venn diagram, all the prime factors inside the Venn diagram. Let's take one more example to understand this better. Let's find HCF and LCM for 105 and 84. For that, let's first break down 105 into its prime factors. 105 can be broken down as 5 and 21. 5 is the prime number, so let's not touch that. 21 can be broken down as 3 times 7. So 105 can be broken down as 3 times 5 times 7. What about 84? 84 can be broken down as 4 times 21. 4 can be further broken down as 2 times 2, and 21 can be further broken down as 3 times 7. Now we have all the prime numbers at the end of the branch. So 84 can be written as 2 times 2 times 3 times 7. Now let's put all these prime factors together. Now the construction of the Venn diagram. So the one on the left represents prime factors of 105, and the one on the right represents prime factors of 84. Let's first put the prime factors in the overlapping region. So if you look at the prime factors carefully, which are the common prime factors for both of them? As you can see, 3 is a common factor for both of them. So let's put 3 in the common region. We also see that 7 is a common factor for both of them. So 7 also goes into the common region. Apart from 3 and 7, 105 has a 5 as a prime factor, which goes into the uncommon region of 105. Similarly, in case of 84, apart from 3 and 7, we have two 2's, which are prime factors, which go into the uncommon region of 84. And now that we have laid out the Venn diagram, let's go and find the HCF and LCM. As you remember, HCF is the product of the prime factors in the common region. In this case, it is 3 times 7, which is 21. That's the HCF of 105 and 84. In case of LCM, it is the product of all the prime factors inside the Venn diagram. That is 5 times 3, which is 15, times 7, which is 105, times 2, which is 210, times 2, which is 420. So the LCM of 105 and 84 is 420, and HCF of 105 and 84 is 21. Why is this method effective for finding HCF and LCM? Because with one method, we get both HCF and LCM. It's like hitting two birds with the same stone. Well, that's the end of this session on prime factor decomposition. If you recollect, we learned what are prime factor decomposition. Okay, how do we do prime factor decomposition for different numbers? And finally, we also learned how do we use prime factor decomposition to find HCF and LCM of different numbers. I hope you enjoyed the session and understood whatever was taught in this. Thanks a lot.